Hello everyone. We have an exciting topic for you today. We'll learn about one of the most powerful generative modeling techniques in modern AI, diffusion models. These models have become the foundation of the state-of-the-art image, video, and text generation, surpassing traditional generative approaches like GANs and VAEs in terms of sample quality and stability. Diffusion models rely on a two-step process, a forward diffusion process that gradually adds noise to the data, destroying its structure over time, and a reverse process that learns to reconstruct the original data by systematically denoising it. Let's begin by understanding the fundamental mechanics of these models. Diffusion models are inspired by non-equilibrium thermodynamics and define a Markov chain of diffusion steps. Each step incrementally adds Gaussian noise to the input data, transforming it into pure noise over multiple steps. The reverse process then learns to undo this transformation by predicting and removing noise step by step, reconstructing the original data. Unlike VAEs or normalizing flows, diffusion models do not rely on a predefined latent variable structure. Instead, they learn a high-dimensional latent representation that is the same size as the original data, leading to improved expressivity and sample diversity. One of the most important contributions in this field was denoising diffusion probabilistic model, or let's call it DDPMs, introduced at NeurIPS 2020. The key components of DDPMs include forward process, a predefined schedule that adds noise at each step until the data is indistinguishable from random noise, the reverse process, a learned function that predicts and removes noise iteratively, reconstructing the original data samples, and variational inference, a probabilistic optimization framework that minimizes the difference between the true data distribution and the learned model distribution. Unlike adversarial models, DDPM offer greater training stability and better sample quality, making them a superior alternative in many generative tasks. Now, let's have a quick overview on training diffusion models, the objectives, and the loss functions. The goal of training a diffusion model is to learn a function that removes noise effectively at each step of the reverse process. This is achieved by optimizing a loss function that measures how well the model reconstructs clean data from noisy inputs. Instead of directly learning the inverse of the forward process, diffusion models use denoising score matching, which predicts the added noise at each step and gradually removes it. The training objective is based on, first, KL divergence minimization, which ensures that the reverse process closely matches the true data distribution. And 2, noise prediction loss, learning to estimate the amount of noise added at each step and subtracting it correctly. Through this process, diffusion models learn to generate data samples that closely resemble real-world distributions. Since the introduction of DDPMs, multiple advancements have improved efficiency, speed, and controllability of these models. Some notable improvements include classifier-free guidance. Instead of relying on external classifiers for conditional generation, this technique modifies the noise prediction process to generate high-quality images conditioned on text, labels, or other constraints. Another is latent diffusion models, or LDMs. Rather than operating directly in pixel space, LDMs apply diffusion in a compressed latent space, significantly reducing computational costs while maintaining high-quality generation. A score-based generative modeling is another one, a generalization of diffusion model that uses a stochastic differential equation to continuously transform data distribution, leading to more flexible generative capabilities. These advancements have led to breakthrough in image, video, and text generation, powering applications such as DALL-E, Stable Diffusion, and OpenAI Sora. As diffusion models continue to evolve, they will reshape industries such as creative media, gaming, medical imaging, and robotics. Future work will focus on making these models faster, more efficient, and adaptable to real-world applications.